Hello, welcome to Lab 3 Circuits. So for the introduction, the goal of this lab was to use the principles of energy conservation, or the loop rule, and the current conservation, which is the charge of conservation and the definition of steady state, to predict the behavior of circuits containing resistors in series and parallel, and using multimeters to measure the actual values of the current and the potential differences in the circuit. And some results preview on the current in the simple circuit was 0.019 amps, and in the RC circuit, the capacitor took 78 seconds to charge and 6 seconds to discharge for a 10 ohm bulb, and this tells us that the RC circuits are time dependent. Some assumptions that we made were that the resistance of the wires are negligible and the resistance of the multimeters are negligible. Some of the important concepts in this lab include the node rule, which is that the current entering a junction will equal the sum of the currents from each junction, and this follows the conservation of charge. So here we have the current in is going to be equal to the current out, and then also the loop rule, which is that the difference in potential of a round trip path is zero, and this follows the conservation of energy, so the change in potential of the round trip is equal to zero. Some more concepts include electrical resistance, so Ohm's law, which states that the change in potential is equal to the current times the resistance, and we can rearrange that to say that the resistance is equal to the change in potential over the current. And when resistors are in a series, the equivalent resistance is going to equal 1 over or sum of 1 over the resistors, and then when they're in parallel, the equivalent resistance is going to be just equal to the sum. And then there's a diagram which shows the resistors in series versus parallel. And then also capacitance, which is how much charge can be stored, and this is equal to the charge on one of the plates divided by the absolute value of the change in potential, which also equals the permittivity constant times area over the distance s. Our system in this experiment is the ammeter or voltmeter, which measures the current and potential difference, and then the surroundings is going to be the circuit, which includes the current and potential differences in the circuit. Here's a look at the setup for the simple circuit. So part 1 was to create a simple circuit and to predict the currents of I1 and I2 from the two 1.5 volt batteries. And so according to theoretical calculations, the current should be 0.0204 amps, and then the actual current, the volts in each battery measured to be 1.4 volts each, and so this led the current calculation to be 0.019 amps, and then when the current was reversed, both measurements became negative. This is a graph showing the potential versus position. So the potential increases at first, and then across the first resistance there's some decrease, and then steady in between the two resistors, and then decreases more for the 100 ohm resistor. And reaches 0. Then the next part of the experiment is the RC circuit, and this is set up with two batteries once again, and then a capacitor and two bulbs, both of which were 10 ohms each, and charging the capacitor took 78 seconds, while discharging took about 6 seconds, and through the charging process the bulb started to glow, and then when it was discharged, the light faded quickly. Some possible sources of error in this experiment were assuming no resistance in the wires, the voltmeters, no air resistance, friction of any kind, basically nothing that would deviate from ideality, and not perfect connection of the voltmeter to the wires, and then any errors inside the voltmeter itself. And then for the what if you charge a capacitor with no resistance in the current, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? And explain. So ideally the capacitor is charged instantaneously in this situation. However, in reality it will take some finite but very small amount of time to charge, and this is because the system is not going to be perfect. The wires are not going to be perfectly conducting, and there's going to be some resistance that prevents the capacitor from reaching full charge in an instant.